Hi everybody, welcome to Calculus to Review. On this side, there will be the formulas and the summary of what we're using for the review. Right. Question 1. Find the derivative of the tangent inverse of that function. Of course, we have the formula for the tangent inverse. We can use that, but let's assume that I'm not using it. Just use what we call the basic derivative of inverse function. So we have the tangent inverse. To get rid of tangent inverse, to undo it, we will take the tangent on both sides. Right. So that gives us tangent of y equal to, that cancel out 11x squared minus 2. Now we take derivative with respect to x, and we assume y is a function of x. So derivative with respect to x, just say it, or differentiate with respect to x. Do that, and we have derivative of tangent is secant square. But since y is a function of x and we differentiate with respect to x, we have to write derivative of y with respect to x. Because y is a function of x, so this is like the chain rule. And derivative on the right hand side with respect to x is 22x. And now divide by the secant square on the other side, and we should have it. So dy over dx is 22x over secant of y square. I will just write secant of y square like this. Right, now of course the answer should be in terms of x. So this is what we do. Originally we have tangent is equal to 11x squared over 2. So I will write tangent of y is 11x squared minus 2 over 1. I need to write that as a fraction or as a ratio, so we can put on the right triangle. The angle being y. Have tangent is opposite over adjacent, and then the hypotenuse is 1 square, which is 1, plus 11 minus 11x square minus 2 square. Right, so that is the hypotenuse. Because of that, secant of the angle y will be equal to 1 over cosine, which is cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. Over 1, or just the square root of 11x squared minus 2 square plus 1. I just flip it for no reason, but that's the same thing. Right, now that is secant. Now we have secant square, so just substitute that into secant. And we have a square root of that plus 1. 11x squared minus 2 square plus 1. And secant square, so that 1 square. And finally, square cancel the square root. We have 22x over 11x square minus 2 square plus 1. Right. So that's what we have. Right. I write out the timestamp, so later on when you watch the video, you can just go to the description and click on the time for the particular problem. Right. Now, there's another way to do that is using the formula on that side. So let me do this. So we have tangent inverse of 11x squared minus 2. Now the derivative of the tangent inverse is 1 over 1 plus something square. So now I just keep the parentheses. The derivative of that is 1 over 1 plus the parentheses square, and then the derivative of that parentheses. So we're using the chain rule with the formula that I highlighted on that side. So we have 11 x squared minus 2 inside the parentheses, and the derivative of 11x squared minus 2 is 22x. So 22x 1 plus 11x squared minus 2 squared. Right, of course you see that should be the same thing as we got without knowing that formula. Right, so that's the first one. Timestamp. Right, the second one, we'll do the same thing, but I will get the sine inverse by itself first by divide by 2. So we do that. Now to get rid of the sine inverse, or to undo it, I will take the sine function right. So that gives us sine of y over 2 is equal to e to the 5t. Right, now once again we differentiate with respect to x on both sides. Derivative of sine is cosine. And then the derivative of y over 2, or 1/2 y, is 1 over 2 y prime. Of course I can write dy over dx, but also y prime doesn't matter. Right, so that is derivative on the left side. Derivative on the right side, e to the 5t. Derivative of e exponential will be the same thing. Where's that? Okay, here. Now we have 5t. So derivative will be a chain rule. So that will be 5 e to the 5t. E to the 5t, the same thing, and then the derivative of 5t, which is 5. So that's what we have. Right, and get y prime by itself. So that gives us 5e to the 5t divided by, because the cosine go to the other side, divide, and then the 2 we move to the top. So multiply 2 on the top on both sides and divide by that. And of course we multiply 2 on both sides. And the 2 cancel here, so that's what we have. So that gives us 10 e to the 5t cosine of y over 2. Now all we need is find out what is cosine y over 2, and for that we draw a triangle. And we use this ratio. The angle is y over 2. Right. Just write over 1 so we have the ratio. Sine is opposite over hypotenuse. So adjacent will be square root of 1 square, or 1 minus e to the 5t square. Right? Or 1 square minus e to the 5t square. That can be rewritten as 1 power to another power. I multiply 5t to 2, so e to the 10t. Right, so that is adjacent. Now we need cosine. Cosine is the adjacent over hypotenuse. Adjacent over hypotenuse. Or just square root 1 minus e to the 10t. Right. So that is cosine. I'll substitute that in here, and that's what we get. Right. Now, of course, we can also use the formula for the sine inverse directly, which is this. So let me write the problem. Y equal to 2 sine inverse of e to the 5t. Now, so sine inverse of something, so derivative, there's a 2 there, of course. Derivative of sine inverse is 1 over square root of 1 minus something square, right? That's what the formulas on that side indicate. And then derivative of the parentheses. That's what we have. Just happen to have e to the 5t inside the parentheses. So with that we have 2 1 minus e to the 10t, and then e to 5t on the top, multiplied, derivative of e to 5t is 5e to the 5t, right? That derivative of e to the 5t, not 2 and 5, right? 10 e to the 5t over 1 minus e to the 10t. Of course, we should get the same thing. 5 times 10. Right. Next we find the limit of this function. So first thing, the first rule of limit is just substitute the number, see what happens. Right? If we put infinity in here for x, three over infinity, a finite over infinity, so that goes to 0. So this will go to 1 to infinity. So this is indeterminate. If it is indeterminate involving the power, so we need to take the log, the natural log. So I start with, originally, just let y be that limit. Right. Then I will take the log or the ln, the natural log on both sides. And instead of right in front of the ln, in front of the limit, we can just put right after the limit. That will be right. The reason we'll take the natural log on both sides because we can use the properties of the natural log to say it. We can take the power outside as a coefficient. So that means we'll take this outside right. Right, so we take the x outside as a coefficient. Next, for most of the indeterminate involving limit, we should use the Hospital rule for most of them. Of course, there's some other ways, more direct, but the Hospital rule should work here. So, but in order to use the Hospital rule, we need something divided by something. Here we just have a product. So we need to bring something to the bottom. So we have a ratio of two functions. So by default, we can say x to the first power. We move that to the bottom, it becomes -2. By the way, we do the same thing, x to the fifth from the bottom, move to the top. I can say x to -5. And then x to the first here, move to the bottom, becomes -1. Right? Now we have a ratio of two functions. Then we can divide them. I mean, we can use the L'Hopital rule. Now this is the L'Hopital rule. And we take derivative of the top, derivative of the bottom, derivative of the top, derivative of ln. Is that it's 1 over something, so it's going to be 1 over the parentheses, and then derivative of the parentheses. Derivative of the bottom is -x to -2, so that is easy. Right. Now inside the parentheses is 1 plus 3x to -5. 1 plus 3x to -5. Sorry, can't run out of space here. Now we continue. Right. Now we have 1 over 3x to -5. And the derivative of this is -15 x to the -6 over -x to -2. Right. Now the negative and the negative here cancel out. Then with 15 x to -6 and x over -2. So what we see here is negative, that's positive. We still have 1 on the top and 1 plus 3x to -5. What we simply find here, oh, there's still 15 though. what we simplify here is we take this term, divide by this term. So when we divide them, we subtract the exponents because they have the same basis. Just subtract the exponent. So that's what we have. So we end up with 15 x to negative 4. That gives us negative 4 over 1 plus 3x to the negative 5. Well, now of course we substitute the infinity here, right? Now, but instead of that, what we do here is we try to get rid of the power here. So if we multiply x to negative 4, if we multiply x to the 4 top and bottom, the reason we do that is x to the 4 and x to negative 4 will cancel out. If we do that, we just have 15 on the top. Right? And x to the 4 times 1. And x to the 4 times this. Right? I can write that as 3 over x. So 15 on the top, the bottom, the x to the 4th, plus 3 over x. Now, as x go to infinity, 3 over x, this will go to 0. We have finite over infinity, so that's just 0. Now x go to infinity, the top is 15, the bottom is infinity. So a finite divided by infinity, so this is equal to 0. So the limit here is equal to 0. Right? Again, 3 over x go to 0 and x go to infinity. So x to the 4th go to infinity. Infinity at the bottom, finite on the top. That will be 0. And finally, we're not solving for that. We solve for, at the end, we will have this. So from that to that and then this. Ln of y is equal to 0. Now we use another properties here. E to ln of something. That cancel out, just m. So now we take the e on both sides. E and ln cancel out. So that is y equal to e to 0 power, which is 1. Now y is that limit, so that limit is equal to 1. Right? So first thing we put in the numbers infinity for x, and that gives us indeterminate. So we know we're going to use the L'Hopital rule. But in order to have the L'Hopital rule, we need to have a ratio of two functions. So that's why we need to take down the power and write that to the bottom. Right? So take ln on both sides allow us to bring down the power and bring that to the bottom using the negative exponent. And then L'Hopital rule, and the rest is just simplifying it. Right, timestamp. Right. Next. Use the limit method to determine which of the two given functions grow faster. So now it goes for the ratio of two functions. I'm just saying f of x, g of x. We have limit go to infinity, right? So if we have the faster on the top, that means the top will go to infinity faster than the bottom. If the top is faster, then that go to infinity faster. And therefore we have infinity over something is still infinity. Now if on the other hand, if the bottom goes to infinity faster, the top's not there yet. Finite divided by infinity is 0. So we just take the limit of a ratio, divide the two function, and then if it is infinity, that means the top go faster to infinity. If it is equal to 0, that means the bottom go faster to 0. And if it is equal to a constant anywhere between 0 and infinity, different constant than 0, then we say they have the compatible rate. Right. So bottom line is I'm just take the limit and divide both of them. Just take one, divide by the other, doesn't matter. And x goes to infinity. Just say that over right. Now if we put in infinity, of course 4 times infinity to the 10, that infinity, and then e to infinity, also infinity. So this one we have infinity over infinity indeterminate. That means we can use L'Hopital rule. So taking derivative of the top divided by derivative of the bottom. Derivative of the top is 4 times 10. I'm not writing 40 for a reason. We'll see in a minute. And derivative of this is 0.6 e to the 0.6 x. Right. Now you see this. We have x to the 9. If we put in infinity, that's still infinity. If we put infinity at the bottom, that's still infinity. So we still have indeterminate of infinity over infinity. So that means we take the L'Hopital rule one more time. Now, bring down the 9. And then we have x to the 8. And then there will be another 0.6. So make it a square. Right. So that still have infinity over infinity. So that means we take the L'Hopital rule again and again. Essentially, we'll take derivative until we'll see that we have 4, 10, 9, 8, all the way until we bring down 1, until we have derivative of x squared, which is 2x, derivative of 2x. Derivative of x is 1, so the bottom is going to be 1. And then here we have 0.6. Every time we take derivative, we have a 0.6, one extra factor of 0.6. So here we have 10, there's 1, 9, there will be 2, 1, so that will be to the 10 power. Right, so bottom line is we have 4 times 10 factorial. At the bottom we have 0.6 to the 10 and then e to 0.6x. Now, the bottom have e to something, right? The exponential function going like this. So as x go to infinity, that go to infinity. So this term go to infinity. 10 factorial is a big number, but still finite. 0.6 to the 10 is still finite. So bottom line is, if we do this, we have a finite number divided by infinity. In that case, will be 0. Now, if it is 0, that means the bottom has to go to infinity faster. So the bottom is e to the 0.6 x. So we say, and we write as follows: e to the 0.6x go to infinity faster, and we use that simple. for x to the 10. Right. Of course, if we happen to flip it, then we should get the same result. So it doesn't matter which one divide by which. If the bottom go faster to infinity, then that would be 0. Or if it is 0, that means the bottom goes faster to infinity. Right, next, let's look at this one. So just take one divided by the other. Just keep x squared on top. Divided by the ln of x squared at the bottom. Right. Then of course, we use the properties just to simplify this. Notice that this is ln of x squared and not ln of x. That completely different things. Now this is the square only on the x. For that, we can bring down the coefficient. So let's just rewrite the problem. Then we have 2 ln of x. Right, now ln of x, so this is e to the x, and ln of x will look like this. So when x go to infinity, that does go to infinity. So when x go to infinity, the top is infinity square, which is still infinity. The bottom ln of infinity, which is still infinity. So once again, we have infinity over infinity indeterminate. So that means we use the Hopital rule, taking derivative of the top divided by derivative of the bottom. Derivative of x squared is 2x. Derivative of ln of x is 1 over x. Now, here we can cancel out the 2. And we have x over 1 over x. Now, divide by fraction is multiply reciprocal. X over 1. So that's just limit of x squared. And now infinity, x go to infinity, so infinity square. So that's going to be infinity. Now, if it is infinity, that means the top goes faster than the bottom. Otherwise, that would be 0. If it is the other way around. Now, so the top goes faster than the bottom. So we say x squared go faster than ln of x squared. So in general, all things being equal, let's just say the power of 2, for example. The 2 to the x will go faster than x to the 2, and will go faster than, of course, any power less than that, and that go faster than ln of x. Of course, there extend to more detail. We may have x to the x, which is the power function or factorial. Bottom line is the exponential function go faster than polynomial. Of course, higher degree of polynomial will go faster than the lower degree polynomial, and that's still greater than ln of x. And that's what we have for that problem. Now we go to different things. Find the area of the shaded region. So if you have this type of problem on the test, we're asking to find the area or find the volume, you can use the calculator. The more important, the one that I test you on this is just how to set up the integral. So if you can set up the integral, and you can use the calculator to evaluate it. So that should not be a problem, right? So now on this one we have two functions that denote. We have the parabola, I mean both of them are parabola. So that one is y equal to x squared minus 4, and this one is y equal to 2x squared plus x minus 6. Right. Now, so you see that actually, sorry, this is right. Good thing we didn't. Okay, so yeah, that should be the case. Sorry about that. Right, it doesn't matter. We want the area of the shaded region, so we're talking about this one. And we talk about this one. Right. Now, the difference of those two regions is that on this first region here, the function above is the red one, the function below is the green one, that one above that. On the other side, for this one, this curve is above the other curve, so that function above that. So we just need to write the integral. Now, for the limit though, from 1 to 2, so that's what we have for this shaded region from 1 to 2. The function above is this function. The function below is x squared minus 4. Right, so that gives us the area for that. Simplify, we have 2x squared minus x squared, so that is x squared plus x minus 6 minus a negative 4, so minus 6 plus 4 minus 2. Right, so we do that. And then this integral from negative 2 to 1. And then we'll take the function on above, which is x squared minus 4. Subtract the function below. So that gives us negative 2 to 1. And x squared minus 2x squared is negative x squared. Negative x. And negative 4 plus, negative 4 negative. Negative 4 minus negative 6. Negative, that turn to positive. So negative 4 plus 6, so that plus 2. Now, so as you see, for this one, we take that function, subtract that function. For this one, the other way around. So since we flip it, we expect to have opposite function in here, and in this we do x squared, negative x squared, x, negative 2, and 2. Right. Now the rest, I just put that in the calculator and evaluate. So, math number 9, we'll go from 1 to 2, x squared plus x minus 2 dx. That gives us, we can change to fraction, 11 over 6. Now for this one, of course we can just do that. And now we just change the limit to negative 2 to 1. And then say what happened to the function? Well, it's just opposite to that. So we just go ahead and do this, and at the end change the sign. So negative 9 over 2. So that should be positive 9 over 2. Right, because they have opposite function. Just throw an extra negative, that will do. Of course, we can just do this. And just insert the negative sign in front of everything. Yeah, that will do. Right, now just want to mention this real quick. If your calculator set up differently, and it asks you to show you this instead, that's perfectly fine. Just enter the function like negative, this is negative, x squared minus x plus 2. The x is the variable that goes from negative 2 to 1. But it gives you the same thing. So the math brain will look better. Right, and then finally we have 11 over 6 plus 9 over 2. And we can convert to fraction. That is 19 over 3. So the total area, so we say the area is 11 over 6 plus 9 over 2 is 19 over 3. Right. There's also another way to do that. The limit go from negative 2 to 2 for the whole region, right? Now, we don't know which function above which function, so to make sure that itself, to get the whatever function here should be positive throughout the interval. So we just throw in the absolute values, so it doesn't matter. If it could be negative, the absolute value will take care of it. Just hit math, absolute values. Just take one function, subtract the others, to x squared plus x minus 6, subtract x squared minus 4. You see, it's the same thing. We just take the absolute values of the difference of two functions. That guaranteed to be positive, or at least 0. But that's what we have, that problem. So times 10. Right, next, find the area enclosed by the given curves. So we have two curves. So first, if we have a calculator, if we want to graph it, it's fine. If not, just plot a few points. Right, so that is the parabola that opens down like that. That goes through 0, 0, and 0, 2, right? So look like and 2x minus 4, right? 2x minus 4, that's easy. When x equals 0, that's negative 4. X equal to 2, that's 0. So 0, negative 4, and 2, 0. Here. So when we need to extend this function, look like the intersections there and there. So we're talking about this region here. Right, just to be sure about the intersection, we just find it. So the intersection, let the two functions equal each other, find the intersection first. y equal to 2x minus x squared equal to 2x minus 4. Right, 2x and 2x cancel out on both sides. We have negative x squared equal to negative 4. So x squared equal to 4. And x equal to plus or minus square root of 4, which is plus or minus 2. Right, so that's easy. We do have 2 and negative 2 as the intersection. And then we just set up the integral for it. The area for this is equal to the integral from negative 2 to 2. The function above is the curve, which is 2x minus x squared. The function below is 2x minus 4. So that gives us negative 2 to 2. 2x minus 2x, that cancels out. Negative x squared, negative, that plus 4. Dx. And now we just evaluate from negative 2 to 2 of x squared, negative x squared plus 4 and we can change the fraction. That's 32 over 3. Right, so simple enough. So whether the region is given, it is important that when we set up the integral, it is the function above minus the function below, and we need to find the limits if we don't have it. Right. Right. Next, we will have the volume of the solid generated by revolving the shaded region about the given axis. Right, so we have this rotate about the x-axis. Right, so this we use the dishwasher method or the shell method. Right, so that's what we have. Right, now when we rotate this, it will look like a shape. Look like that. Right, now we can use the dish or the washer method or the shell method. On this one, I'm just going to use the dish or the washer. Particularly, we see that the region is, the axis rotation is part of the region. This is the axis of rotation, which is the region, belong to the region itself. Right, now, so because the axis of rotation is the part of the boundary, this is going to be a disk method, so we use the disk method. Let's start with the disk method. That's the form of the disk, and the limit determined later. That's why AB is generically like this. Now, the H, we need to determine if it is dx or dy. Now, if it rotates like this, the axis of rotation, if we stack the disk, it will be, the disk will look like this. And there's another disk. So the disk, the increment or the dx or dy here should be parallel to the axis of rotation. So once again, for the dish and washer method, the axis of rotation will, let me say that again. Whereas dx or dy, it will be aligned with the axis of rotation. This is the x-axis, so we align to it. So it's going to be dx here. Now, as far as limit for x, obviously go from 0 to 2. That's the region. That's the region R. Now we just need to determine What is r square? Well, r is from the axis of rotation to the edge of the region, so that's just the function. Right? So we have the function above, which is that parabola. Subtract the function below the x-axis. So we have this is r, the distance from the axis of rotation to the edge. For this method, that's what we have. Right? Of course, we can pull out pi. Right. And just like what I mentioned previously, for this type problem, just need to set up the integral. The rest we can just use calculator to evaluate it. There will be a lot of problems that we integrate. Alright, from 0. And if there's a pi, take it out. Just enter those numbers. 4 minus x square dx. So we do that without the pi. And at the end, we just put the pi back to it. Right. So, once again, the height in the this or Weierstrass method, or the x or dy, will align with the axis of rotation. It is horizontally, so it will be horizontal increment. So that will be dx. And when we determine x, it is dx. We know the limit, and you just need to determine r, which is the radius from the center, from the axis of rotation to the outer edge. Right. Next, we have this, but rotate around the y-axis. Well, turn out both of these are. So actually, rotation is this one. Once again, this is part of the boundary. So it is this method again, because the boundary, including the axis of rotation. Right. So this method is still the same thing. Now, the axis of rotation is vertical, so the increment or the dx dy must align to it. So that will align vertically. So that will be dy. So we know for sure that it's going to be dy. And we know the limit for y will go from 0 to 3 for that region. Now just need to determine this. Now, r is from the distance, is the distance from the axis of rotation to the edge. The edge is this function. However, we have to enter in as a function of y, so we need to solve for it. Give it 3x and divide by 3, so y squared over 3 is equal to x. So here we have to put that in here, the function on the right minus the function on the left. So that will be just y squared over 3. So that's it. Now, if we have this problem and we rotate about the x-axis, then we have the inner radius and the outer radius. But in this case, it's this method, so there's only one radius. And then again, we can fat out the pi. and then we just have y squared over 3 square dy. 0 to 3 y squared divided by 3 square right 27 over 5, then stick a pi to it. So this is just this method because the axis rotation in the boundary. Right. That is this method. Next, we have the shell method. Now, if this region rotates about the y-axis, by the way, the shell method, let's go with the formula first. Two pi r h and t. Notice that the h here is different than the h on this Washer method. Right, so determine. First, is this a dx or dy? By the way, the axis rotation is the y-axis, so rotate about the y-axis. Right, so the same method, unlike this method or Washer method, is called the slicing. So this one is wrapping. The shell method, we're just wrapping around like this. And because when you're wrapping like this, the thickness is perpendicular to the axis of rotation, right? So if we wrap something around it, the thickness, or think about like a roll of papers, the thickness of the paper will be perpendicular to the axis of rotation. So if that is the case, the axis of rotation is vertical. So the increment here, t, is going to be dx. The thickness is going to be dx. Right, so at the integral, it's going to be 2 pi r and then h. The t is dx. Now for this one, the region go from 0 to 2, so that's the limit. Get that out of the way. Now what is r and what is h? Now the different r here is different than what we have on the previous one as well. So in this case, because we wrap around it, r is whatever a point is. So to find r, I pick a random point. Say this point has the x and y coordinate, very generic. Any region, any point in the region. And then r is the distance from that point to the axis of rotation. Because if this point is x and y, this is the x coordinate. So that should match with the variable there. So it is x. Now the height will be the difference of two functions. So that will be the height. The function above is square root of 2x. The function below is just 0, right? So the height is different of two functions, and the r is the distance from the axis of rotation to a generic point. Zero to 2 pi x square root of 2x dx, right? Again, I'm going to take out the pi. I'm just going to say 2x square root of 2x dx. Right. This will not go to fraction. Right, so that 3.999999 something. Right. And then just take a pi to it. So this more like 6.4. Yeah, 32/5. We can use that. But I said, in this case, just set up the integral. That's more important. Right. That's what we have. Next, I'll use the same method for this region. Again, I'll start out with the formula. Two pi r h t. Axis rotation is the x-axis. So we're wrapping around this. So the increment will be perpendicular to it. So t is going to be dy. So 1 is going to be 2 pi r h, but it's going to be dy. And y for this region from 0 to 5. Right. That's what we have with to work with. Now, determine r. Just pick a point here, any point in the region, and the distance from that point to the axis of rotation, that will be r. And for that point, of course, r is equal to y. And then the height. The height is different of two functions. The height will be parallel to the axis of rotation. So think about this. If we have a roll of paper or toilet paper or paper towel, the height will be the width of the paper, not the thickness, but the width of the paper, right? So we just take this function, the function on the right, which is x equal to y squared over 5. And then the left is 0, so we just have y squared over 5 minus 0, or just y squared over 5. And then with 2 pi y squared over 5 dy. Right, we can simplify by taking the 2 pi and 5 outside. We just have y cubed 0 to 5. Right, just do that. Actually, I'm just say 2/5. I just leave the pi outside by itself. So 2/5, and then the integral from 0 to 5 y cubed 62.5 125/2. And then we stick a pi to it. Right, so that is the shell method. Right, next we combine this together and we do both, either shell method or dishwasher method for the same region. Right, so first use both the same method and the dishwasher method for revolving the region. The region is the triangle 0, 0, just plotting the point 0, 0, 0 and 2, x equal to 0, y equal to 2, and 1, x equal to 1, y equal to 2. x equal to 1, y equal to 2, sorry. Right, 0, 0, 0, 2, and 1 and 2. So we're talking about this triangle. Now let's do the shell method first, and we'll do this in washer. This all washer. Right. By the way, it rotates about the line x equal to 1, which is the vertical line. Now if it is a vertical line for the shell method, we're gonna go perpendicular to it. So the shell method is gonna be dx. So I'm just say v equal to 2 pi r h t. This particular it's gonna be dx. And the x of the region go from 0 to 1. Now we determine r, then we determine h. So pick a random point. Let's label that x and y. And the distance to the axis of rotation. That distance is going to be x. Right? Of course not. Now let me zoom in and then talk about this. This distance is x and y, and what we want is the r here. Now, the x actually is distance to the y-axis, so this is x. What we want is r. The whole thing is being 1. So r in this case is going to be 1 minus x. Right? Because x is the distance to the x-axis, not the distance to the axis of rotation. So that is x, and the distance from the point to the axis of rotation, that is r. That's what we want. So that r is equal to 1 minus x. And then the height is the difference of the two functions. By the way, the function on the top is y equal to 2. The bottom is y equal to 2x. Right? When x equal to, this is y equal to 2x. When x equal to 0, y equal to 0. When x equal to 1, y equal to 2. Right, so that's what we have. So let me rewrite this again nicely. Pi 0 to 1, 2, 1 minus x, 2 minus 2x dx. So that is that is the shell method. Just get a calculator, find the values from 0 to 1, 2, 1 minus x, 2 minus 2x dx. We have the limits. Yep, we have the limits. Right, that 4 over 3 pi. This problem did not ask for the values, but we find it anyway. Now for this washer, first we have to draw this region again. This is y equal to 2x. Now the axis of rotation is the x equal to 1. Now, as you see, the axis of rotation is not part of the boundary, or the boundary does not include the axis of rotation. So that must be the washer method, meaning there's two radius. Sorry, it's not the x, it's just h in general. Right. the axis of rotation is vertical, so we stack it, so that's going to be dy. So we have something square minus something square and dy, y being going from 0 to 2. Right, now there will be 2 radii. From the axis of rotation to the outer edge, that is the big radius, which is 1, right? That distance is constantly 1. The little radius is from the axis of rotation to the inner edge, so it will be that distance. And that distance is the difference of 2 functions, the vertical line and the slant line. But everything have to be in terms of y, so I will switch this as y over 2 equal to x. Now, the function on the right is x equal to 1. The function on the left is y over 2. Right? So this distance function on the right minus function on the left. So that's what we have. So simplify this, pull out the pi, 0 to 2, 1 minus y over 2 square dy. Right, let's evaluate that as well. From 0 to 2, and we have 1 minus, I'm just use x instead of y. Sorry. It is a square there. Yep. Right. And stick a pi to it at the end. Should be 4 over 3 pi as well. Of course, both methods should give us the same area. I mean the same volume. At the shoot. Right, that's what we have. That one. Now do the same thing for different region. Now this one is y equal to x squared. That is the parabola. Y equal to 4. Horizontal line. And x equal to 0. The y-axis. So we're talking about the region here. Right, let's do the shell method first, and then do the dishwasher. Right, now the axis of rotation is y equal to 5, so that is the horizontal line here. Y equal to 4. Right. And x equal to 0, which is the y-axis. Right, so we're talking about that region rotating about the horizontal axis of y equal to 5. Right, now the shell method, the general formula v 2 pi r h t. The thickness is perpendicular to the axis of rotation, horizontal, so that the t is going to be vertical, so t in this case dy. Right, so we set up the integral 2 pi something for r, something for h, and then dy, where y go from 0 to 4. Right, that's what we come up with. Right, next, the r, the radius. The radius is just a distance from a point. I pick up any generic point. And r is the distance from the axis of rotation to that point. So we're looking for this, which is r. Now, with respect to that point, this is x, this is y. So we have y. The whole thing is 5. So if we want r, it's going to be 5 minus y for r. And then the height is the difference of two functions. And different of two functions should be horizontal like this, because the height is always parallel to the axis of rotation. So we talk about this. So the function on the right minus the function on the left. It have to be in terms of y though. So we have to solve for it. Y equal to x squared, so x equals square root of y. So square root of y minus 0. The function on the right minus the function on the left. It must have the same variable as the x or the y here. Right, pull out the pi. Alright, evaluate that. I'm just use x instead of y. Right, just keep that for a moment. Remember, there should be a pi to it, multiply to it as well. Right, so like 27.733. Usually, when estimate there's some errors, and usually that will be the case. Right, for 16 over 15. I just keep that in the back pocket. What was that? For 16 over 15. Right, now let's do that for the dishwasher method. Now, the height. The height is always aligned with the axis of rotation. By the way, for the dish and washer method and the shell, one of them is dx, the other one is dy. So this one dy, this will be dx. And indeed it is aligned or parallel to the axis of rotation. So it's going to be dx. We have the radius, the big radius square minus the little radius square, and then dx, and there's a pi. Dx, limit for x go from 0 to 2 here. Right, so that's what we have. Now the big radius is from the axis of rotation to the outer edge. So y equal to 5 above minus the below is x squared. That's the big radius. And the little radius is from the axis of rotation to the inner edge. 5 minus 4. Right? When we rotate, axis of rotation to the outer edge, axis of rotation to the inner edge. And put our pi. We have 5 minus x squared minus 1 square, just 1. Right, let's do that. Right, keep the pi outside. Going from 0 to 2. 5 minus x squared. Square. What happened? 5 minus x square minus 1. Right, as you see, that's the same thing for 16 over 15. Right, so both of them give us for 16 over 15 pi. But we should get that. Right, so both of them should give you the same volume. Right, next we have the arc length. Right, so arc length formula over there could be either x or y, but it's just one square root of 1 plus derivative square. Right, so it's easy. Now we have y equal to that from this value, so obviously we're going to use the x values here, right? So the arc length 1 plus derivative in term of x square and going from dx go from 0 to 5 over 4. Right, now the function is that so derivative, bring it down, 2 and 2 cancel out, we have 3x. The derivative is 3x. I substitute that in here. 2x to the 1/2, sorry. Take the 3/2 down. 2 and 2 cancel out, and then 3. And the original power minus 1. So that's what we have. Right, substitute that in here. That gives us 1. 3 squared is 9. So just 9x dx. Right. So again, let me just write the integral to evaluate from 0 to 5 over 4. Integral of 1 plus 9x dx. With a square root like that, I don't think this one will come out nice and even. So let's just do this by hand. By the way, let's check real quick. Just keep that in the back pocket. This one I use substitution. Let u be the inside the square root here. So take derivative. Move the move the dx. And then divide by 9. Right, now as far for the limit, originally x go from 0 to 5 over 4. When x equal to 0, u equal to 1 plus 9 times 0. So that is 1. And when x equal to 5 over 4, u is 1 plus 9 times 5 over 4. So 9 times 5 over 4, so that is 45 over 4. which is 49 over 4, by the way. Right, 49 over 4. Right, with that, we continue the integral. Now the u will go from 1 to 49 over 4. Square root 1 plus 9x is u. Dx is that. Right, so I can bring out the 9. And square root, I can write 1/2. Right, integral of u to the 1/2 is u to the 3/2 over 3/2. Integral from 1 to 49 over 4. Right, now divide by 3/2 is multiplied by 2/3. 9 and 3 cancel out. I give us 6. U to the 3/2 going from 1 to 49 over 4. Right, of course we just substitute in 49 over 4 to the 3/2 minus 6. Substitute 1 in there. Right, this should come out nicely. 49 over 4 to the 3/2. (343 over 8). And then just minus 6. So that's what we have. 36.875. Right, what did we say we have earlier? Right, so obviously there's something off here. Right. Of course, I'm glad I checked. I forgot there's a 6 in here. Right. So where is the problem? Right, so this one's correct. I don't see there's a problem with the substitution. Right, let's just do this and see what happens. Right, I see why. This is divided by 9 and I put multiply by 9. So this is 1 over 9. Sorry about that. 1 over 9 and 2/3. So 2 over 27. Right, so it's not 6, but 2 over 27. Right, let's do that again. 2 over 27 times 49 over 4 to the 3 halves minus 2 over 27. Right, we should get the same thing as before. So that's good. So let me write this again. 2 over 27. 49 over 4 to the 3 halves minus 2 over 27. And we can even get a fraction out of it. Let's see from the beginning, can we get a fraction out of it? Very good then. Right, so once again, I'm sorry about that. Right, next, setup. Do not evaluate the integral for the length of the curve. So now this one has function of y and we have the limit for y. So naturally we're going to use the formula that has y in it. Derivative go from 0 to pi over 4. Right? So that should be easy. Derivative of tangent. Okay, so we have the function is 3 tangent of y. So derivative is 3 secant square. So we have 1 plus 3 times secant square, and then we square again. That gives us 1 plus 3 square is 9. Secant square again is secant to the 4th. Right. Now this one we will not evaluate the integral. So it's just going to live like that. Right. Next. Evaluate the integral. So this one we have two different type of function. So usually those are the either substitution or integration by parts. Now, usually if it is substitution, when whatever we let equal to u, derivative of it will be part of the problem. I'm just going to demonstrate so that we quick. So something like this is a substitution problem, because if u equal to x cubed, derivative of x cubed is x squared. So this one is a substitution problem. Right. So this one, if we let u equal to 2x, derivative of that is 2. There's still an x out here, so it's not good. So we're just going to use integration by parts. And integration by parts, there's an acronym. So the log, inverse trig, polynomial or algebraic expression, trigonometry, and then exponential function. So here we see the polynomial first, so that is going to be u. I prefer to use the table derivative and to be integrated. Whatever appear first on this we use to be u or to be differentiated. So that will be negative 6x plus 1. And then the other one is e to the 2x. Right, derivative of this is negative 6. Derivative negative 6 is 0. And after that, it's going to be 0. Integral of e to the 2x is 1/2 e to the 2x. And then integral of this is 1/2 up to 1/2. So that is 1/4 e to the 2x. And we don't need to go any further than that. Right, so that equal to, right, iteration by parts. We just want to draw it in the organole. The first one is positive, the next one is negative, and everything after that we're alternating size. But we don't need any other diagonals because here we have 0. Everything after that would be 0. So the first one is negative 6x plus 1. And then 1/2 e to the 2x. And then subtract negative 6, 1/4 e to the 2x plus c. The rest is just simplifying it. I'm just going to factor out e to the 2x. Then we have 1/2 negative 6x plus 1. And then minus negative, that's a plus 6/4. We can simplify that later. E to the 2x. Right? Negative, that's 6 divided by 4. Right, now we can factor out e to the 2x. And then we have 1/2 negative 6x plus 1. 6/4 is 3/2. Let's see. Right. And now we multiply this out. Negative 6x, and that is negative 3x. 1/2 times 1 is 1/2 plus 3/2. Right. Of course, you can just stop at this step or that step. The key point here is to use the iteration by parts, and we should arrive to this at least. The rest is just simplify the problem. Right. Next, we have also this problem. Also, iteration by parts. Right. So we have try to write smaller because this might take a lot of space. Right. So we have the part that is to be differentiated and the part that is integrated. So we just choose whatever appears first on this list. So there's no log, there's no inverse trig, no polynomial. Then the next one is a trig. We do have the cosine for x. Take derivative of cosine for x is negative 4 sine of 4x. And then derivative of this is negative 4 cosine of 4x. And if we keep doing that, it's not going to be 0. So it's not going to be 0. Right, now e to the 5x, integrate 1/5 e to the 5x, and another 1/5. So 1/25 e to the 5x. Again, it's not going to go to 0. So there must be something else if it's not vanished. Right, first, that diagonal positive. By the way, I'm going to say it, this integral is I. It's easy to do that. Now, the integral I equal to that diagonal cosine of 4x 1/5 e to the 5x. And the next diagonal minus negative 4 sine of 4x. Note that in the integral, of course, you have the derivative and integral for general. If we have the constant multiplied to it, for derivative it's going to be multiply, for the integral it's going to be divide. Right, so subtract, for that subtract negative 4 sine 4x and 1 over 25 e to the 5x. Right, we cannot do this forever because this will not go to 0. So if we want to stop, and we will stop with, by the way, the next line is going to be positive, so positive, negative, positive with an integral. So if we want to stop, we have to draw the integral sign to stop. Then we say, why don't we stop at the first step? Well, the reason we stop at the second step, because what we see here is very familiar. Sorry, kind of very small here. Right, so let me simplify a little bit, maybe we have more space. By the way, we can just write that down. So 1/5 e to the 5x cosine of 4x minus the negative, that's a plus 4 over 25 e to the 5x sine of 4x. I'll take out the negative 4 and 25. What's left is cosine of 4x and e to the 5x dx. Now what we see here is the exact integral as beginning. Right, so that's why we do it two steps, because the integral, I mean the derivative of cosine and sine, derivative of cosine is negative sine, derivative of negative sine is negative cosine. So it doesn't matter where we start with sine or cosine, if we take derivative 2 times, it will go back to the same function, right? If we have sine from the beginning, derivative will be cosine, derivative will be sine. So after 2 steps, it will get back to the same function, but opposite though. Bottom line is, that's what we have, right? Right, so if I equal to 1 over 5 e to the 5x cosine 4x plus 4 over 25 e to the 5x sine of 4x minus 4 over 25 I. Now we solve for the integral I, so I move that on both sides. We have 1I plus 4 over 25, so that is 29 over 25 I. So 1 plus right 1/5 e to the 5x cosine 4x 4 over 25 e to the 5x sine of 4x. And to get back to I, we multiply the reciprocal, which is 25 over 29. 1/5 e to the 5x cosine 4x, 4/25 e to the 5x sine 4x. Right, just like in any integral, just plus a constant c at the end. Right, so when we have the integral of e to the something with the trig function, we're going to use integration by part twice and then stop, because if it is the trig function, it will not vanish, so we have to stop. So whenever we stop, if we do it 2 steps and we stop, we should get back to the same function as before. So that's why we can solve that algebraically like this. Right, next we have this. Once again, if this cosecant squared, we can integrate that. But there's x in the way. So again, this will be integration by parts. If this is 4x squared, then yes, this is substitution, but it's not. Substitution will not simplify this x. So to be differentiated, to be integrated, and the list, there's no log, no inverse trig, but there's the x polynomial. Derivative of x is 1, derivative of 1 is 0. Now cosecant. Now cosecant, the integral of cosecant square is negative cotangent. And there's a 4, so we put that divided by 4. Cotangent of u, which is 4x. Right. The cosecant square. Now, an integral of cotangent is going to be that. Again, but then there's a 4, so we want to put another 1/4 ln sine of 4x, and that's all we want to go to, because the diagonal, everything after that will be 0. So the first one's positive, and then this negative, and everything after that will be 0. So that's all we have. Right, so first x times negative 1/4 cotangent of 4x, and then subtract 1 times that's negative 1/16 ln of sine of 4x, of course plus a constant c. So that gives us 1/4 x cotangent of 4x plus 1/16 ln sine of 4x plus c. Right. So that's all we have for that one. Next we have ln of 9x. This is definite integral, so there's a limit. We need to evaluate that as well. Right, so every time we have the ln, I should say most of the time when we have the ln, that is integration by parts. Right, So to be differentiated, to be integrated. And let's check. There's a log, okay? That's the first thing we see, ln of 9x. And then we don't have anything on that side, so we just have to put 1. Right, derivative of ln of 9x, well, what's the derivative of ln? It's 1 over reciprocal, right? By the way, you can write this ln of 9 plus ln of x. So derivative of this is just derivative of ln of x is 1 over x. We will not go no further than this because that's not going to go to 0. And again, this is not going to go to 0 in the integral. So the derivative of ln of x is 1 over x. And then of course we can say that x to negative 1 if we want to. Then keep going. But that does not give us anywhere. Right. So usually this one, I'm not going to write equal, just say in the integral I. We just integrate first and then at the end we evaluate the limit. So if we do that without the limit, integration by parts, positive. So we have ln of 9x times x. And then if we keep going like that, it's not going to go anywhere. So we have to stop. And we have 1 over x. And then x dx. Right? So that gives us x, ln of 9x. And x cancel here, which is 1 dx. And that gives us x, ln of 9x minus x plus c. Now the integral does have the limit, so we just have to use limit 1 and 3. So we just said x, ln of 9x minus x going from 1 to 3. Substitute 3 in for x. And substitute 1 in for x. Right. So that 3 ln of 27 minus 3, and that is ln of 9 minus the negative, that's a plus 1. To simplify this, we have 3 ln of 27 minus ln of 9 minus 3 plus 1 minus 2. Right. Let's see if we can check our answers. From 1 to 3, ln of 9x. And we have that. Now, how about this? 3 ln of 27 minus ln of 9 minus 2. Right, so we're good. Right, next problem we determine should we use the integration by parts or substitution. Right, so the rules of that is the simplest rule is if we cannot use substitution, use integration by parts. So the part of that is if we let u equal to something, derivative of that should be included in the problem. Now, if we let u be negative x here, derivative of that does not cancel with this. So if substitution doesn't work, you integration by parts. And if it is iteration by parts, use this to determine the u. So iteration by parts on this one, and no log, no inverse trig. There's a algebraic expression. So u is equal to x squared minus 2x plus 5. That is the derivative. The integral part is the other one. I mean dv is e to the negative x dx. Right. Next one, like I said, most of the time when we have the log, that's going to be iteration by parts, because that will be the first one on the list. So u equal to ln of 7x, and dv is 2x dx. So this is iteration by parts. Iteration by parts. Right, next, this one. Can we use substitution? By the way, on this one it cannot be iteration by parts, because for that one we cannot integrate it. So usually when we see cosine square, cosine x cubed, or sine, or a to the x square, something complicated like that, that iteration by parts. I mean that iteration by part will not work, so we have to use substitution. Because when we let u equal to x cubed, derivative of that is x squared, cancel nicely with this. Right. Once again, if you see x squared, x cubed, I mean, if you see e to the x squared, sine x squared, I mean, if we see this, or cube, or this, any higher power than 1, that most of the time is substitution. And we can confirm that if we use substitution, that cancels nicely with x squared here. Alright, for this one, well, what do we have there? By the way, I just made a simple modification here, and that we can use iteration by parts, because substitution doesn't work. So this works just like that one. U is equal to 7x plus 3, and dv is e to the negative x dx. The last one is sine inverse. Well, that also high on the list, so that is also iteration by parts. And dv is just 1 dx. Right. And that's what we have for this problem. I think I stop here on this video and then pick it up on another video.